So I'll say it again before we start in a couple of minutes, but just a reminder or a heads up for everybody that we will be recording today's meeting. So if you ask us sort of a question in the chat and I call it out, so you could expect that to make its way into the recording, and then this will be posted to the CNS Western Branch page at some time following this webinar. But I'll give a few more minutes for everybody to kind of trickle in before we kick things off. Okay, here we go. So I have a noon Eastern time by my watch. So we'll kick things off. So hello everyone. Thank you for coming forward to the CNS Western Branch webinar today. So a few housekeeping things to begin with. So for today's talk, it will be recorded, and we will be posting this to the CNS site on the Western Branch page sometime following the presentation. Also, when it comes to the Q&A, I ask that people use the chat for any kind of questions. It's kind of just easier keeping everything within the chat in terms of both discussions and questions. And so I myself will be sort of moderating the chat and then asking the questions of Chris for the end of at the end of his presentation. Some other things. So I'm pleased to announce that this year we'll be holding a Western Branch kind of AGM at the annual meeting. Since the Western Branch is so large, it's hard for us to have the general gathering on a yearly basis outside of the AGM, and so that there'll be a room and an announcement for that for anybody who's in the actual Western Branch for us meeting and deciding on our new executive and some sort of general outlook stuff. So with all of that, let's get started. So my name is Arthur Sidham. I'm the co-chair of the Western Branch and the assistant professor at the University of Regina in small modular reactors safety and licensing. And I'm pleased to introduce you to Chris Ress. So Chris is a highly experienced safety and assurance engineer with over 16 years of experience. Chris started his career in 2007 with British Nuclear Group. Since then, he has worked with various industries in the UK, Australia, and Canada, including space, oil and gas, automotive, nuclear, and academic research. His experience focuses on conducting safety assessments for high hazard facilities and safety critical systems, including nuclear reactors, decommissioning activities, waste storage facilities, spacecraft, oil pipelines, autonomous vehicles, and nuclear research. Chris is currently employed with Risk Tech Solutions Canada as a technical expert in nuclear safety. Chris has also spent over a decade lecturing in universities on nuclear disasters, safety cases, and atomic and nuclear physics. He is currently finishing a part-time PhD in near space flight risk engineering, focused on radiation risks from space weather effects. With that, I'd like to hand it over to Chris.
Thanks, Arthur, and thanks for that introduction. Good morning, all, and thank you first of all to the CNS for setting this one up. So I will just bring up presentation. So yeah, good morning, good afternoon, depending on where you're based. So yeah, I'm Chris Rees, technical expert in nuclear safety, and again, thanks to the CNS for putting this one on today. Today I'm going to be talking to you about the evolution of safety analysis or safety cases and how they can help in enhancing risk mitigation, specifically in the nuclear industry. So the contents of today, what we're going to hear about, we'll give you a little bit about Ristex. That's who I work for at the moment. You might not have heard of us, and I'll give you a bit of background and some of our nuclear expertise just to set the scene a little bit. Then we'll talk about the history, the origin, and the methodology of all around safety analysis in the nuclear industry. The importance of safety analysis not only ensuring regulatory compliance, but ensuring robust risk mitigation, so we will go home safely at the end of the day. We'll present some case studies and the safety analysis challenges behind some of those case studies, and some of those are worldwide, some in Canada, some in Europe. And then we'll discuss sort of the scalability and analysis efforts for decommissioning activities, as well as operational and new build and the hazard analysis behind that. And then we'll talk about the future and evolution of safety analysis with the likes of digital safety assessments and the use of AI and machine learning, and some conclusions around safety analysis. I like this little picture here. So yeah, my accent, I am based in Canada, but I am from the UK originally, as Arthur said. So I'm very much a big fan of Marmite. So if you do see Marmite in the supermarket, you either are supposed to either love it or you hate it. And so similar, I think, with safety cases, you either love them or hate them. So by the end of this presentation, hopefully you'll love them a little bit more. So Risk Tech Solutions Canada. So I'm based out of Calgary, and we've been operating in Canada since 2011. And we have a number of offices in North America. Some facts about us. So we currently have about over 300 full-time employees, 16 offices across the world. We work across a number of industries, so transport, defense, nuclear, clean energy, oil and gas. So we work with various different companies and clients on sort of high hazard, high risk industries. And we'll talk about some of the nuclear examples today. Some of our sort of consulting services, just to give you a little bit of a background on where we're coming from. So nuclear safety side of things, which we're going to talk about a lot today. So safety case authoring, safety analysis, planning, hazard identification, deterministic probability risk, HF, and consequence assessment, and then nuclear security, culture and behavior, and we do some training as well, as well as some consulting. And I'll put the links to our sort of various pages for LinkedIn and for our website at the end of the presentation, so you can have a further look. Oh, bit too far. So the evolution of safety cases. So we need to set the scene first of all. We need to understand where safety analysis comes from, why it's important. So safety analysis, or sometimes safety cases, we refer to them as one and the same here. It originated in the field of high hazard industries, such as nuclear, aviation, and chemical processing. The concept gained more prominence in the late 20th century as a systematic approach to assess and manage the risks associated with complex and potentially dangerous operations. Now, the idea is to provide a structured document or a safety case that outlines the safety measures, the risk assessments, the safeguards that you claim that are in place to ensure that there's a safe operation within these high hazard industries. And the approach is designed so it enhances that transparency, that accountability, and that regulatory compliance in high risk activities. So to understand the role in modern risk management, we need to understand where safety cases or safety analysis comes from. Now, looking back to sort of the late 1980s, Piper Alpha was an offshore oil platform operated by Occidental, I think that's how I say it, I probably said that wrong, but petroleum in the North Sea. It was at the time, it was one of the largest and most complex platforms in the North Sea. And on the 6th of July 1988, an explosion and fire destroyed the platform completely, killing 167 of 226 crew on board. Now, the explosion itself was caused by a leak from a pump that was temporarily removed for maintenance, and there were several factors that contributed to the incident, including inadequate safety procedures, lack of proper communication between staff and in emergency arrangements, the design of the platform, so the location of the crew quarters was in close proximity to sort of operations and the explosion itself, and the emergency response systems and actions. Following this, the Cullen inquiry made 106 recommendations to the North Sea Safety Programme, and the disaster prompted significant changes in regulation and practices, leading to the introduction of safety cases. So that's why it's important, Piper Alpha. That is where the modern term safety case or safety analysis really comes from. And just a couple of the photos here. So the top right one here shows Piper Alpha before, and then the bottom one, Piper Alpha during sort of the fire and explosion. So quite a catastrophic incident. So following on from Piper Alpha, we saw safety cases and safety analysis being brought in across a number of different industries, including the UK Ministry of Defence. Now, important again to learn how the evolution of safety cases progressed is looking at some of the incidents. So the Nimrod MR2 was a Royal Air Force or RAF maritime patrol aircraft, shown here in the picture. Now, it had a safety case for operations and subsequent safety analysis to support that, and risk management, risk assessment, and safeguards. On September 2nd, 2006, the Nimrod was on patrol in Helmand province in Afghanistan, and it suffered a catastrophic mid-air fire. And this was only minutes after it had completed air-to-air refueling, and it led to the complete loss of the aircraft and death of 14 on board. So the explosion itself was attributed to the fuel system, namely fuel leaked onto a hot element. And the inquiry concluded that the safety case for Nimrod was fundamentally flawed, and effectively it was just a paper exercise. You know, it's a large stack of paper. There was little control for modifications on the system, maintenance, or true safety oversight from the Ministry of Defence. Further, the inquiry recommended that safety cases should be renamed as risk cases rather than safety cases, and that they should be shaped, so they should be succinct, they should be homegrown, they should be accessible and proportionate and easy to understand and document light, so not safety case in paper. And they recommended the simple definition of a risk case as a reasonable confirmation the risks are LARP or as low as reasonably practical levels. So safety cases, we need to understand the evolution to understand where we are, to understand where we're going, and Piper Alpha and Nimrod are some of the key incidents that lead to us where we are now. So since the creation of safety cases, there have been many myths or misconceptions about safety cases, some reflecting the difficulties in the 1980s and 1990s, and then later, and the incidents like Nimrod and Piper Alpha that we discussed. So further, there is this conception that the safety analysis that you do is just for the regulator, where in reality, the case is developed by the operator, for the operator. At the end of the day, we all want our staff or our employees to go home safe, and that safety analysis is part of that, to go home safe at the end of the day, irrespective of what you're demonstrating to the regulator. So safety analysis represents good practice. It is the working document to improve safety produced by those who have the most knowledge. That's one of the key things. It's produced by people who understand the plant, understand the operations, the plans, the build, etc. So while in the US, the NRC still requires quite a prescriptive approach for nuclear assurance, some of the ANS and the American Nuclear Society recommendations is called for a risk-based, performance-based regulations. So we might see that starting to evolve, and we do see that starting to come in more, and arguing that risk-informed regulations use insights for probabilistic risk and things like that to focus safety resources on the most risk-significant issues, thereby achieving an increase in safety while simultaneously reducing unnecessary regulatory burdens. So we're not sending everything to the regulator, we're actually doing some deterministic assessment as well. So where do we sit at the moment in the Canadian nuclear market? So current safety analysis in Canada. So I'm sure some of you on the call will be aware of the regulatory regime and how it sits, but for those that are not, this is an overview. So Canadian nuclear sites are governed by the CNSC, so the Canadian Nuclear Safety Commission, and that sits under the Nuclear Safety and Control Act. So the CNSC provides the regulatory guides for licenses and how to comply with regulatory requirements. So how do we, if you're operating a nuclear site, how do you comply with the regulatory requirements? How do you get a license to operate? The safety analysis for a proposed activity or facility is covered by the CNSC Reg Docs. So they include advice on hazard identification, safety measures, etc. And all nuclear sites operators in Canada must present a strong case to obtain a license from the CNSC. And the safety case is part of that, and that includes the documents on how the regulatory requirements are met or exceeded. These documents cover all the major safety areas such as physical design, human performance management, safety analysis, waste management, radiation protection, etc. And then the safety case needs to be maintained and updated through the facility's life cycle. So that might be construction, that might be operation, that might be decommissioning. And the assessment will include both a deterministic and a probabilistic safety assessment. So how do we actually go about the safety analysis? So we know that we need to produce a case, we need to produce a strong case that shows why all our control measures are identified, all our hazards are identified. So this section will discuss the methodology for safety analysis, presenting a systematic and a comprehensive approach to hazard identification, risk assessment, and identification of safety measures. So in our nice little pie diagram / wheel, it shows steps 1 to 7, and they present the steps for the development of a comprehensive suite of documents that will form the basis of the safety analysis for any nuclear activities. This includes a systematic and comprehensive approach to hazard identification, to risk assessment, and identification of safety measures. And in the next couple of slides, we'll discuss each of these sections and the ideal safety analysis as part of that. So step 1 is that hazard identification. So we're identifying the potential hazards associated with operation of the system or the plant. This can be done by various hazard identification techniques. We sort of HAZOP, FMEA, SWIFT, so failure modes effects analysis for FMEA. SWIFT is structured what if technique, so asking the questions, what if this happens, what if that happens, and these various hazard identification techniques are scalable to the level of hazard presented from the proposed activities, and we'll talk a little bit more about that later in the presentation, but that becomes key for sort of going forward and the best practice safety analysis. So step 2, risk assessment. So we're going to assess the likelihood and the consequences of the identified hazards. We're going to use deterministic or probabilistic risk assessment. And when we say likelihood, we mean how often is this going to happen a year? You know, are we going to have an aircraft impact once a year, or is it going to be once in 10,000 years? Are we in an earthquake zone? Are human operators going to get things wrong? we're flawed as humans. We get things wrong quite a lot. So what are the performance? What's the likelihood of things actually going to happen? And then the consequence, what's the radiological consequence in this case for nuclear? So specifically, we would then look at deterministic and probabilistic risks of where we can screen things out. So deterministically looking at them, and then when perhaps we can't, looking at the probabilistic risk to determine the tolerability of the identified hazards. So safety measures, step 3, so identification of safety measures. Now, we need to establish the safety requirements and the standards based on the level of risk associated with hazards. So if we have something that's very low risk, low hazard, we're not going to have a very robust safety measure against that because it's not required. So it might be something procedural, etc., etc. If we've got something that's high risk, high hazard, then we may have engineered controls, we may have shielding in the case of radiation, things like that. So we have to scale those safety requirements and safety measures partly to what the requirements to bring the doses down to acceptable levels, but partly for regulatory requirements as well. So here we would look to identify, assess, and implement those safety measures and those controls to mitigate the identified hazards and record that in our safety analysis. So step 4, one of the key ones. So we've produced the safety analysis. We've started to build our case of why our plant or activity is safe. Then we need that verification. So we need that independent review and the verification of assessments and case. And then we look for that regulatory or an internal approval of the case as well. And then step 5, so we've got our case, we've done our internal verification, but then the design changes, the plant changes, the activity changes. So we need to implement a process to review the status of the case or the analysis and ensure that it remains live. Now, keeping that case live or keeping that analysis live forms a crucial part of the process because any modifications to the proposals of the plant can change what we previously said. So we need to ensure that we are keeping that case live, we actually access it, we actually keep it up to date. And then communications and training, step 6. So communication of the safety measures, claims from the case to the key stakeholders. We'll talk a little bit more about this later on, but if we make claims from the analysis that an operator is going to do X, Y, and Z, they need to be aware of that. We need to communicate to our stakeholders what we're going to do, what safety measures we have, and how we actually perform. And then the final step of the analysis of the case is the closeout. So the closeout of the case itself and the associated documentation. This ensures that the current state of the plant, the systems, etc., is captured and any claim safety measures are removed. So we're not leaving things in onerous for future. Further, the lessons learned from the project are actually captured for future works. And then documentation, we can compile all those that safety case documentation, and we can actually finally close it out. Okay, so we've spoken a little bit about setting the scene and where we are and how to get best practice and how we actually do safety assessments. We've got a number of case studies today that we'll talk through and some of the safety analysis challenges behind that. So the first one is a site that I worked at. So this is Hinkley Point in Somerset in the UK. We were talking about the interim storage facilities and the safety cases behind that for Bradwell, Berkeley and Hinkley Point nuclear sites. And this is the first interim storage facilities for Magnox, who operate the sites. So Magnox Limited, they've just rebranded as Nuclear Restoration Services, but they constructed these stores when they were still known as Magnox. They're responsible for the safely decommissioning the first generation of nuclear reactors and research sites across the UK. And here we focus on the safety analysis for new plant or interim storage facilities to support the decommissioning activities, specifically at the Bradwell, Berkeley and Hinkley sites. So the interim storage facilities are designed with a lifetime of 50 to 100 years. They're constructed alongside reactor sites, so they're still on their licensed sites. The photos you see here show in construction and complete loading. So the top right one is interim storage facility in construction, and the bottom right we've got a concrete waste package being loaded. Now, the challenges for safety analysis behind these interim storages is that they are quite unique. They're new. They are holding new types of waste packages, and these waste packages are varying types. So some are concrete, some are ductile cast iron, some are square, some are round. They are all sort of different shapes, and they hold a number of different waste types. So production also for analysis and a case that will be for a store that's in operation for 50 to 100 years, including inspection and monitoring regimes. So that had to be included as well. We had to look at the impact of potential external events over extended period of time. So rising sea levels, earthquake risk, de-staffing of the site is part of the concerns for safety and security, because if you imagine most of these sites are going through decommissioning, there won't be anything left on those sites, so they will be largely de-staffed. So how do you maintain security, etc., and how do you maintain the case whether you haven't got many staff on board? They're regional stores, so they have slightly different decommissioning timelines, and they have slightly variations in design and size. They have varying waste types, so some of these are they're primarily all intermediate level waste. Some of them are wet, some of them are dry. So how do you process that? How do you store that? And then the licensing challenges, so the case for construction, a separate case for construction, for operations, and for storage. And the second case study that we'll talk around today, so the safety analysis of Norwegian nuclear decommissioning activities at NND. So in 2018 and 2019, the 2 research reactors in Norway were permanently taken out of operation. And NND is an agency under the Ministry of Trade, Industry and Fisheries in Norway, responsible for decommissioning of the research reactors and other nuclear infrastructure. So NND is responsible for safe handling, storage and disposal of nuclear waste in Norway itself. So the use of previous assessments for safety assessment and engineering processes that were appropriate for new operation for operational plant were not appropriate for decommissioning activities here. So what we had, if you imagine we've got procedures and analysis for an operating plant, and then we move into a decommissioning phase, the hazards are not the same. So once the fuel is removed, you've got a different hazard profile, and therefore the procedures that you use for sort of assessment for operations may not be appropriate for decommissioning. So deterministic safety assessment criteria, for example, that was used to prevent core melt was unsurprisingly onerous when applied to comparatively low consequences associated with decommissioning activities scenarios. So some of the revised strategies that come out of the challenges were, the screening out of faults with low radiological consequence. So what we talked about a little bit earlier on, a scalable approach to safety analysis, considering the use of safety measures that are lower in the risk reduction hierarchy, defining a safety classification scheme that avoids overclassification of engineering structures, emphasizing the role of optioneering plays in both cost-effective solution, but also that safety justification. So including safety analysis and safety engineers in that optioneering, and ensuring that supporting evidence such as design substantiation is appropriate to the robustness and extent of the associated risk. So case study 3 we'll talk about today is the Canadian-based terrestrial energy molten salt reactor and the preliminary safety analysis and siting report. So Ristec were involved in developing and authoring the molten salt reactor vendor design review for phase 1 and phase 2 submissions to the CNSC, and this was for the Darlington site. So some of the challenges behind this, so it's a first of a kind advanced reactor design, so there's little precedent and failure data associated with that. It had some novel challenges to model passive safety systems and failure modes of the safety systems, such as the reactor vessel itself. It was the first reactor in Canada to go through the VDR assessment with the CNSC, and the concept design was changing. So we had those modifications coming in, so constant change in design, and which could often significantly affect the safety analysis that was done. It also was set in a scene where there were changes in the regulatory regime, especially sort of security side of things, and the developing of SMR guidance from Canadian standards point of view, but also from the CNSC. So there was a significant opportunity here with this sort of safety analysis to apply a risk-informed design. So the early development of PSA was able to feed into the design options and analysis requirements, and demonstrate, secure by design and also safeguards by design principles. And then the last case study that we'll talk about today is Sizewell B. So Sizewell B is an operating PWR site, and we'll talk about replacement of the condensate tanks and the case behind that. So for those who are not aware, so condensate tanks, or CSTs, they're important structures for temporarily storing condensed steam before going into the steam generator after it returns from the turbine in a pressurized water reactor, so PWR. Now, some of the challenges here, so this was the development of a safety case strategy first off, before even any of the analysis was done, and then looking at the safety functional requirements and substantiation reports for this condensate tank. So this was replacement of the tanks. They're critical infrastructure, so they have to be maintained and still operational while the replacement is going on. And this required multiple submissions to the regulator, covering construction, foundation, deconstruction, tanks, pipework across the board, a lot of different areas. And then demonstration of nuclear safety during construction, where you've got new tanks adjacent to existing and operating plant. Hazard qualification for extended feed water pipe work, and then development of a commissioning plan that aligns with a tight timescale. So this was an operating plant, and this demonstrates, some of the things we were talking about: control of modifications, control of impact on adjacent plant, and then multiple submissions to the regulator. So where do we see the future of safety analysis, and what areas can we focus on? Excuse me. Firstly, we need to note that, in addition to the new build and operations, there is a significant decommissioning problem worldwide. With the number of reactors already in decommissioning and an aging fleet, so we have 70% of reactors worldwide are older than 30 years, 25% of reactors are older than 40 years. This problem is only going to get bigger. So safe decommissioning activities must be completed successfully in order for new reactors to be constructed, and we need to maintain that stakeholder support. So if we don't have the stakeholder support, and we can't show as an industry that we can actually decommission reactors, we're never going to move into a future safety world. So, like I said, not only the demand for decommissioning will increase, but also we have to keep new build in mind and how we successfully decommission this. And we should be under no illusions, the decommissioning phase in the nuclear industry is very different to the previous stage. So the hazards might be lower, but the challenges are unique. What can we bring to that decommissioning problem? So safety cases for nuclear decommissioning need to evolve to the unique challenges of shutting down reactors and safely dismantling nuclear facilities. The evolution of safety cases or safety analysis typically involves some of the key considerations we've put here. So removing of safety systems that we could potentially erode defense in depth. So we need to keep that in mind, that things that were claimed during operations, perhaps now we are going to start removing, but we need to look at defense in depth. We may introduce new activities and associated hazards. So we're going to be breaking into areas that perhaps were never intended to be broken into. We're going to be removing waste that was planned for very long-term storage or was never planned for retrieval. Accurate characterization of radioactive waste. So a lot of these plants that were built in the 60s and 70s, that we need accurate characterization data of what is actually put in some of these vaults or storage areas. And it's a focus on waste management opposed to power operation. So it's a different mindset. We are taking things apart, we are knocking things down, we are managing the waste opposed to continuous operations. And then things like periodic safety reviews, so looking at the state of the plant periodically and revising that safety analysis. And then wider considerations, we've got an aging workforce, the operations have ceased, we may have people retiring, people leaving, we have a knowledge drain, aging plant, upkeep, maintenance, and then challenges of waste retrieval. So I was talking to Arthur before this presentation, and I think the CNS last year gave a presentation where they said they needed 5,000 to 10,000 new engineers just for Canadian nuclear industry over sort of the next decade. So that is a lot of people to bring in, a lot of engineers. So wider challenges and the future of safety analysis. So we've got challenges from first of a kind safety assessments for novel works, for SMRs, for new reactor designs, and the challenges around continued operations as well as waste management and characterization. So what are some of the evolving or new tools and methodology that we can look at to bring to some of these new designs and these new problems, even in operations and decommissioning world? So deterministic and fault tree analysis. We've talked a little bit about deterministic assessment and how that can screen out faults, but also probabilistic risk side of things. That integration of human factors. So something that was not considered in sort of the 1960s, 1970s design of human factors and ergonomics and safety claims behind operator interactions. We can bring that into the design, but also into the safety analysis. Safety and security concerns. So that's something that we see more and more in safety analysis and the associated cases, that a lot of these sort of sites are lower staffings and lower levels of securities. We don't have armed guards, etc., etc. So what's the safety justification about that? And a holistic approach to decommissioning activities. So when we say a holistic approach to decommissioning activities, what we mean is that they then start to consider environmental impacts, industrial safety, not just nuclear and radiological. The use of AI and machine learning to identify potential safety risks in activities. And then the use of digital safety cases. So, and we'll talk a little bit more about that in the next coming slides. And then carrying on, so the wider challenges and opportunities for us going forward: regulatory compliance, so evolution of the regulatory regime, funding for new build, but also for decommissioning activities, and ensuring that the analysis we do is fit for purpose and there is value in that safety analysis. We've talked a little bit about the human resource and the staffing to actually continue operating some of these plants, but also moving into sort of the new world. We've got aging infrastructure. We need to look at emergency preparedness from those sort of legacy hazards. And then the regulatory landscape, so risk-informed regulation, where we prioritize those safety critical issues, and then we look at deterministic and probabilistic risk assessment, possible flexible licensing strategies, continuing that stakeholder engagement throughout the whole process of that we talked about, steps 1 to 7, but also that wider international collaboration, so sharing of knowledge, best practice. So just to start to wrap up a little bit, we'll talk about the future of safety analysis, and we'll just pick on a couple of those key areas that I talked about before. So namely, we'll talk about electronic live safety cases, or e-safety cases, which is very nicely demonstrated by our Legends of Risk Tech here. So you must be our new electronic safety case officer. I hope he doesn't look like that, but we'll talk about what an e-safety case actually looks like. We'll talk about integration of protection measures and the claims from safety analysis. We'll talk about operationalizing a case and engaging the workforce, and then a succinct and scalable safety analysis. And this is all while still engaging with that regulator or other key stakeholders, and then learning from the wider industry. So electronic safety case, or an e-safety case concept, has been around for a long time. It's struggled to gain widespread traction, perhaps because of its perceived complexity in the past, and the need for bespoke software. In reality, these days, we see sort of electronic safety cases with relatively simple software and make them a lot more accessible. But its purpose and the information presented remains the same as a traditional safety analysis, i.e. to describe the case for safety. For example, identifying the most significant hazards and controls available to ensure the risks are acceptably low. It includes safety critical equipment and human actions that need to be taken. The key difference between sort of your stack of paper though and your e-safety case is that it's interactive. You know, the diagram that we've got here, you can see that you can click links. This means you can navigate, you can connect to the information. So this is a RiskTech example. It's available on sort of an iPad or an iPhone, so a tablet side of things. And the idea is it's accessible anywhere on site, and you can just click and see the relevant information. But in developing that case, we need to say who are the users, you know, who needs what information and at what level, and how is that information accessed. So the level of sophistication and interactivity can be tailored for an e-safety case and to suit the organization intended use. So for example, if we were producing an e-safety case for submission to the regulator, they would focus on sort of the key hazards, and leading through the arguments to show that they are a LARP or a LARA, whereas an operator may be more interested in understanding the day-to-day critical context of their day-to-day roles. You know, why shouldn't I push that button? Why do I need to push that button? Why is that shielding there? What's protecting me? So in order for a safety case to be effective, the information and the document and any supporting document studies need to be available to the people who need to use them. So the protection measure claims are key. So managers will need to see an overview, what protection measures they've got claimed out on plant. Engineers will need to see the details under their relevant discipline or their job and understand why the things that they've got in their area are important, where they're claimed back to that safety analysis. So that's where sort of e-safety case comes in. They can trace that golden thread back to that safety analysis. You know, why is it important that I push this button when I push this button? Because it does X, Y, and Z, and it's claimed in the safety analysis, and that all links back to our license to operate. So further barrier management allows those responsible for managing and maintaining the barriers to understand and to record progress. So for future developments in safety analysis, we see sort of the use of Bowtie software to visualize safety measures, controls, but we also see an integration of maintenance management systems and barrier auditing as well into that sort of protection controls. And then operationalizing your safety case, so engaging your workforce. So once that case is delivered, there is an opportunity to truly embed it in day-to-day to operations. And we need to think about how do I use it and what's expected of me. So the aim of that operationing is to provide the right information to the right people in the right way. So what a technician might need to be aware of or understand is quite different to what their supervisor might need to be. So we would look at sort of a rollout. A level 1 would be an awareness for the sites of posters, etc., leaflets, etc. Level 2 would be an understanding of those safety critical roles and more specific targeted training. So it would depend on what your role is and what you're doing. And then level 3 of knowledge would be like your detailed copies of the case and something that you're using day in, day out. So if they're unsure of something, they need to know why there's a claim in there or why there's an assessment in there, then they can look it up within the case itself. So succinct safety analysis, we talked a little bit about this and learning from Nimrod. The basic function of a safety case document is to provide that information to the stakeholders and demonstrate that you are being safe in your operations, as is kindly demonstrated by our Legends of RiskTech here. So the minister would like to know why all this paper needs to be carried in a safety case. They're very similar to the Nimrod, a giant stack of paper, not an operational safety case. So the problem we've seen in the past is that it can have safety cases that are very large, so they're very large, difficult to navigate, and this leads to a concept of that sort of paper exercise, you know, as the Legend of RiskTech is showing very well here. Some of the best safety cases in reality have a relatively small amount of information, and they make reference to detailed reports, so they reference out to that information rather than including into it. So that comes back to that shaped safety case. And then finally, scalability. So the time and effort spent producing a case should be proportionate to the risks. So we talked a little bit about that earlier with sort of our screening things out, but it should be proportionate to the risk presented by the facility and the operation. So a small plant with a high fatality potential may need more effort than a very large plant with a low fatality potential. And we shouldn't be afraid to screen out faults with justification and documentation. So rather than doing that paper exercise, we can screen things out. We just need to justify and document like that. and then working on that culture where operators believe that every study needs to be completed. So we do need to do a safety analysis, but what is that level of rigor and justifying why? Okay, so starting to wrap up now. So we'll just talk about some of the safety analysis conclusions for today. Like Arthur said, you'll have a copy of this presentation afterwards, and if there's any sort of things that I've brushed over today, we can please feel free to reach out afterwards. But successful safety analysis for nuclear. So we need to embrace a dynamic safety analysis strategy across our nuclear operations. We need to note that nuclear decommissioning is a challenge, as well as operations and new build, and legacy is going to be a growing problem across the world in terms of sort of the more plant and the challenges presented behind that, and to ensure that they are safely, cost effectively and timely completed. Otherwise, no one is going to give money for new operations if we can't decommission the old ones. And then that good practice and lessons learned can help us meet those challenges. So from every stage of the life cycle for a plant, we can look at sort of early gathering of critical information as part of that scaled approach. And we can use some of that wider learning and sharing of worldwide industry. So some of the lessons learned from history that we've touched on today, we've got that scaled approach to safety assessment from sort of Nimrod, and then the continuous improvement in analysis and assessment process, so using new techniques, using new methodologies, using new technology advancements, so AI and machine learning. That greater regulatory alignment and guidance, so working closer with the regulator, but also that international collaboration, so the CNSC working with the NRC and the ONR across the world on aligning, especially where designs of new reactors are sort of being proposed across the world now. And then continued stakeholder engagement through the process, so we maintain that buy-in from not just our regulator, but our stakeholders on site and off site, to show that we're doing a good job with safety analysis and case production. And then use of new methodologies we've talked about a little bit for hazard identification. And then finally, the use of digital safety cases, especially with an aging plant and a workforce. You know, that knowledge drain is real, and it is going out the door. So when we have that sort of use of a digital safety case, where we have that accessible knowledge, it will be beneficial in good practices going forward. Okay, that is the end of our presentation for today. I've rattled through a few things, some of them are a little bit high level. There's my contact details on there, along with our business development manager, and I will hand back to Arthur, but please feel free to reach out if there are any queries. Let me stop this one.
All right, perfect. Great, thank you very much, Chris. It was a great presentation. So for any questions, I just remind the audience that you can post them within the chat, and you can also send them to me privately if you don't want them being for your name to be known for the actual question. So the first one I have here for you, Chris, is regarding your slides. Do you want it just for people if they have questions, they want a copy of your slides, they can reach out to you? You think that's probably better?
Certainly they can do both, so I'm quite happy for them to reach out to me directly, or I think Laura, who's the CNS host today, is recording as well, so they'll have access both. But yeah, I can put my details back up, or whatever they like.
Okay, perfect. So if anybody would like a copy of the slides, they can reach out to Chris, and then of course the recording itself will be up on the CNS site. Good. So I guess I'll just start off by asking a question myself. So one thing you talked about a little bit was the sort of the aspect of the vendor design review. So this is something that we've seen the CNSC implement, and Terrestrial Energy was the first ones out the door to submit for that. I guess in terms of that process, did you find that the significant that the process that this sort of changes in terms of the actual vendors modifications it was easy to accommodate in that overall process when it came to building the safety case for the vendor design review, or is that something that sort of the overall process is a little bit cumbersome for?
I think looking at Terrestrial Energy, I mean, they were unsuccessful, unfortunately, at Darlington for their reactor design, but I think it was a learning process, but I think the process did accommodate it quite well. But I think it is those challenges going forward of how do you cope with changes in the design as things progress. And I think things will get better, and we'll get better at sort of analyzing new designs and sort of new proposals and things like that. But I think the process did work quite well there. But certainly it is a challenge from sort of here's my baseline design and there are going to be things that change, and it's how do you control those modifications, how do you control those changes, especially as you're going through a design process. But that all forms part of that sort of safety analysis and your internal procedures for modifications controls.
Fair. So I guess I'll take the next question here, and this is maybe one with a little bit more of an international outlook. So a lot of risk text work on the decommissioning cases are done over in Europe. So the UK and the Netherlands or Norway are the two examples that you brought up. So in Canada, we've only just relatively recently gotten some clarification on how sort of the ownership process will work for intermediate level waste, which is of course a large sort of consideration when it comes to decommissioning activities. Do you think that is there lessons that Canada should be drawing from some of these other cases? I'm particularly thinking of something sort of like the Magnox case in the UK, where there's lots of a sort of experience they've got with decommissioning and intermediate level waste repositories.
Yeah, certainly. I know. I mean, they all face the same challenges. Magnox is a little bit unique in that they dissolved some of their fuel in the 1980s and stuff, so they've got some sludgy plutonium-loaded waste, so their stores have to be a little bit more shielded and robust for certain areas and certain waste streams. But yeah, there are lessons to be learned, especially with things like the deep geological disposal facilities. So Europe is a little bit probably ahead of Canada at that on the moment. And I think they are, like the NWO is having discussions with the relevant agencies in Europe on sort of the lessons they can learn from that, from the safety analysis point of view and the sort of hazards that they're facing for long-term storage. But yeah, definitely for sort of interim storage, it depends on the waste streams a little bit, but there are lessons to be learned on sort of package container, package design and things like that. I think the UK and sort of Germany have gone through that pain of sort of package design for interim storage, and the likes of sort of Canada can learn from that, definitely.
That's fair. I guess one question that sometimes comes up is the sort of the question of package design for intermediate versus long-term storage for particularly for something like intermediate level waste. Is this something where you think that there's sort of a direct lesson to be drawn from in terms of how best to sort of stagger that for planning?
Yeah, definitely. I think because if you look at sort of like the German case, they sort of ductile cast iron containers for intermediate level waste, and they will sort of put them in a salt mine and then they're grouted in. Whereas the UK is storing them above ground for 50 to 100 years and then wanting to sort of dispose of them because they don't have a disposal facility for long-term storage at the moment. So the safety analysis is different if we bring it from that sort of side of things. You then need to look at a package that's going from the site to the disposal facility. That's a relatively straightforward assessment. Whereas Magnox is saying, actually, we want to keep it for 50 to 100 years above ground before we put it into our disposal facility that we don't know what it's going to look like yet. So you have to write a case and you have to do analysis based on some assumptions for the future, but also noting that you've got a 50 to 100-year storage problem for a container that perhaps wasn't really designed to just be stored above ground for 50 to 100 years.
Yeah. Okay. We're getting some good questions in the chat here. So from I'll start with you, Thomas. So Thomas really asks to find that the nuclear industry adopts more conservative assumptions in implementing this methodology than other industries that you have described. Sorry, the first sort of part of his comment is I find that all the different hazard identification methodologies come down to an expert judgment of whether a system will or will not fail in a given credible scenario due to limited publicly available OPEX information. And in your experience, do you find that the nuclear industry has a more conservative outlook when it comes to that a professional judgment?
Yeah, I would probably say there certainly is a little bit on that. So there are various reliability databases that we can look at for failure rates and things like that. We have a reasonable amount of historic data for nuclear operations. So in that side of things, it's a little bit more than engineering judgment. It's looking at, how often has a nuclear rated crane failed, things like that, and we can then apply some numbers. And then if we look at sort of things like even like human factors, we could say, well, we all make an error and everything goes wrong and we're very conservative, but we can actually do some more detailed calculation behind that and actually substantiate the claims we're putting on it. So would I say they're slightly more conservative than maybe like oil and gas and aerospace? I would say it's proportionate to the level of hazard, so I think that's probably the best way I can justify it. The example with Nimrod, with the MOD, with it being a paper-based exercise, that, as tragic as that accident was, it's one aircraft loss, and with nuclear, if we have an incident, we're talking of sort of hundreds to thousands of potentially impacted, and the long-term effects from sort of contamination and things like that. So it's proportionate to the level of hazard, but we do have the ability to substantiate stuff more than just sort of saying, well, I think it's going to fail, because I've worked here for 40 years, and a little bit like one of those risk tech diagrams and risk tech legend, it's never gone wrong to this point, so therefore it's fine. It's more than that.
It's very interesting, especially the parallels to the aviation industry. I think is one that often gets brought up for good reason. Okay, another question here from Bill. So I think this is referring to one of my previous questions about the waste streams. So what are the current international thoughts on disposal of waste contaminated materials? I think Canada was intending a deep storage recoverable for future processes that may be developed. Are most countries thinking in a similar way? And then he has a sort of a follow-up. What about new concepts for transmutation to stable elements, probably high level materials only? So I think that's some of the work we've seen, lasers and whatnot. Anyway, maybe some thoughts on that.
Yeah, I mean, CNL gave a presentation yesterday, Lunch and Learn, on some of their sort of in situ disposal for some of their early reactor designs, and I think they have their near surface disposal facility, which just been approved, but also looking at sort of test reactor disposal in situ. So that's probably the most relevant for sort of Canadian side of things. The other one I've worked on is Australia. So ANSTO, they have a similar sort of in situ disposal at the moment because they don't have a route for anything. So they've got a couple of test reactors. They don't have a route for disposal at the moment, so it's a lot of in situ thing. With regards sort of Europe, we see sort of vitrification side of things, so it's sort of saying about reuse of things, so turning things into glass for long-term storage, processing of waste, or even metal recycling, so metal melt on some low-level contaminated things and then reused in the nuclear industry again. So that's probably the best examples I can think of the top of my head.
Okay, fair enough. It's sort of I think one question that sometimes comes up in my mind is if some of these SMR designs will end up using in situ disposal as part of their decommissioning case. But I think that's sort of an open question in many ways. The question here from a Paul Sidoran. So Chris, in predictions of the probability of worker or public fatality, are they ever calibrated using actual deaths?
So yes, they are. So there will be an acceptable level of risk basically for site operations. So that might be one fatality in sort of every 10,000 members of the public or something from normal operations, and that will come down from sort of ICRP guidance. So ICRP will say for every CVERT that we give someone, there'll be 5% of a chance of death, or 5 deaths effectively from that. So that level of risk for site operations will feed down from that. So they are based on historical sort of things like Hiroshima, nuclear accidents, things like that. So yeah, they're based on the best available data, that sort of ICRP guidance, and you'll see that worldwide that will filter down into sort of CNSC regulations, even the NRC, and then European regulations as well.
Okay, good. Just a sort of reminder, people, we're gonna go to the sort of the top of the hour, and then we'll kind of cut things off there. But yeah, we're getting a lot of good questions in the chat. So another one from Alex C. In your experience, what elements of performing a safety case cause the greatest delay, and how could these be improved?
Oh, good question.
Mm-hmm.
What elements cause? I think it's probably that transition I've seen from operations to decommissioning. So where, to use a UKism, we would say you do a Rolls-Royce job of the safety case for a decommissioning world, and in reality, that level of hazard isn't as high. And it's that mindset, that transition from operations to decommissioning, where you have to present a case, but with a proportionate hazard assessment. So that's probably the biggest delay, I would say, is seeing that transition across. With regards to sort of operations or new safety cases, it can be the major delay can be the changes in design. So if the design isn't frozen, and if that keeps evolving, that can cause delays in the safety analysis going forward. But probably those are the two that sort of spring to mind from recent experience.
Fair enough. So we have another good, very topical question here from of Daniel. He asks, can you provide some examples of the applications of AI and machine learning on the development of these cases, and what are the regulations supporting the use of these technologies?
Yeah, so probably the only real one I've seen example of at the moment is external events. So releases off-site and looking at sort of AI sort of interface to look at how can actually an off-site release. So if you have an accident on site, you assume a plume goes X, Y, and Z, and members of the public are exposed, etc. But actually using sort of AI and machine learning to look at the direction of that plume, the likelihood of it, and more, where will that actually go? With regards sort of regulation of it, I'm not up to speed at the moment on sort of where the CNSC stands on it. I know that we've had some discussions about bringing in machine learning and AI side of things, but it's that justification again for how are you know, if you're going to use machine learning and AI, why is it appropriate, or why is it giving you a better answer or a worse answer than what you had before? But primarily I've seen it used for external hazards, so looking at offsite releases.
Okay, so really bleeding edge stuff there in terms of what, how this might play out. I'm sure that'll be talked about in the years. So another question from a Mitch Meyer. It's a relatively new process, but is there an example of a Canadian VDR process leading to licensing?
Sorry, can you say that one again, Arthur?
Sorry, it's he's asking if the Canadian VDR process has ever actually led to licensing.
Oh, so yeah, so the Darlington TEI one that I discussed today didn't get selected, so that didn't go forward. So I can't speak to another successful one at the moment that we've been involved with directly, I'm afraid.
Okay, fair enough. Yeah, maybe a little bit outside your wheelhouse. We're getting a last couple of questions in here. Unit A, PSA currently an important topic. This is an interesting one from Alex. So is multiple unit PSA currently an important topic in Canada?
Ooh, multiple unit PSA. So interesting question. So I would
Mm,
say that yeah, it's definitely a consideration, isn't it? Just looking at some of the designs going forward and some of the proposals that are coming in. At the moment, the sort of SMR designs that we've been looking at are sort of single unit PSA sort of side of things, but certainly I think it will come into play depending on the siting and the location and whether even SMR side of things, but even full scale reactor new design you see in the US as well. So yeah, I think it will come into play.
okay, fair enough. I'm gonna take one last question, and this is going to be sort of a combination of what Bill has asked here and then what Mel has asked. And this is in regards to sort of workforce, a general sort of training. We've been talked about needing 5,000 new engineers on the job. Sort of Bill's comment are retiring workers being effectively listened to when it comes to that transfer of knowledge. And Mel's comment here is when it comes to sort of the transfer of knowledge. So you mentioned 5,000 new engineers are needed in nuclear. My own company is experiencing that with many new engineers being hired from university, and the numbers in experienced engineers supervising these decreasing dramatically. So you're seeing a sort of a ratio imbalance. New engineers out of uni do not have ASME code knowledge or a NIN destructive examination experience. Both of these are critical component integrity. How is this accounted for in the safety analysis?
Yeah, that's a very topical question,
Mm,
it's a difficult one. There's a lot of knowledge going out of the door. I think you do see it with the likes of certain CNL. They have an alumni and they do keep in touch with their relevant staff, but unfortunately, people age and knowledge disappears with age. So it is a tricky one. With regards to safety analysis, what we're starting to see more and more is that digital recording of safety, safety analysis and safety cases associated, but also the references and supporting information. So some of these plant, designed in the 60s, built in the 70s and the 80s, the drawings are not electronic. They are not. It's getting better and better, but previously some of them were on like microfiche and stuff. So you have to then bring that into a modern world where it is digitally accessible. So it's that handover from experienced staff to junior staff and things like apprenticeships, but getting people interested in safety analysis. Certainly we have struggled historically, and I can talk about Australia and Europe, to bring people into safety analysis. It's not seen as a glitzy field. It is very much that Marmite jar of you either love it or you hate it. And to bring people into that world, to train them up, it is tricky. And I don't know where we're going to get 5,000 to 10,000 new engineers just in Canada, let alone the rest of the world that's recruiting. If you look at the US, even if you look at China and the builds that they've got going on, where they're going to come from, I don't know. I think we can just say the use of for a safety analysis point of view, that use of digital safety cases and that knowledge bank that you have is critical.
Good. It's that's very insightful. I think that's something the industry is going to be struggling about, and maybe a good topic for a future presentation about workforce development. One last thing I'll throw out here. Bill comments, Marmite's great. Okay, so with that, I think we're gonna wrap things up here. So thanks, Chris, for a great presentation. There's lots of accolades in the comments I haven't gotten to mention. So for everyone again, so we're for those sort of who arrived a little bit late, the Western Branch is looking to hold an AGM at our annual, the overall CNS general meeting. So look out for an email about that from either myself or Chris in the future. And then if you are interested in potentially giving a seminar through the Western Branch, if you think you've got topics that are relevant to sort of nuclear development out west, feel free to send myself an email. And maybe that's something that we can sort of work into a larger schedule. Anyway, thank you everyone for coming again. And so you can expect this video up on the CNS site in sort of maybe about a week or so. Great. Thanks everyone for coming.
Thanks, Arthur. Thanks all.